Ladies and gentlemen, professors and researchers, thank you very much for joining me today for this poster presentation. My name is Ray Wu, a doctoral student at University of Massachusetts Lowell, working under the guidance of Professor Xinwei Wang in the field of fiber optic sensors and their applications. Today, I'm excited to share with you our current work on structural health monitoring using fiber optic sensing technology, especially focusing on the application of Boolean optical time domain analyzer in creating a distributed strain sensing system integrated within a bridge girder. Structural health monitoring is a critical field that involves of collection, interpretation, and analysis of structural data to ensure the safety and integrity of various structures. Fiber optic sensing technology has emerged as a promising solution for precise strain and temperature measurements. Its applications span across diverse fields, including railways, oil pipelines, and highways. In this poster, we will present an innovative approach that utilizes the optical time domain analyzer, short as BOTDA, to establish a distributed strain sensing system, which we have integrated within a fiber-reinforced polymer bridge girder. By measuring the Boolean frequency shift along the entire length of the optical fiber, BOTDA can provide precise spatial information about changes in strain or temperature. This distributed sensing capability allowed us to monitor structure in real time, detecting and pointing potential issues, making the BOTDA a valuable tool for ensuring the safety and integrity of various infrastructure systems. From Figure 1, it shows as a drone photo of the Grist Bridge, which serves as a focal point of our structural health monitoring project. In this image, you can see the entire bridge structure, and the red box indicated that our sensing section. Now let's dive into more details of our sensor design and installation process. Our sensor design comprises a single mode fiber in orange color for distributed temperature sensing, and a U-shaped fiber for BOTDA system. In Figure 2 illustrates the schematic of our textile design, with both sensing sections having a length of 21 meters in each. Additionally, we install a launching fiber at the beginning of the textile to establish a connection with the equipment positioned above the bridge. This configuration allowed for efficient installation inside the bridge girders and protecting the fiber sensors. Typically, bare fiber sensors are challenging to fix on a flat surface and requires meticulous alignment of tiny fibers. However, by embedding the fiber into textile, the installation process was simplified, and a more precise alignment was achieved. This design also allowed for efficiency installation, ensuring accurate data collection and reliable protection for our fiber sensors. The successful installation of our sensing textile at Great Mill Bridge in Hampton was a significant achievement. To optimize efficiency within the limit space of the bridge girders, we employed a modified slider as an invaluable installation tool. This slider facilitated a smooth unrolling of the sensing textile while epoxy was applied for secure bonding. The epoxy was carefully distributed using a brush to ensure even coverage, and any bubbles presented were removed using plastic scraper blades. This process was repeated until the entire bottom surface of the girder was covered with sensing textile. Figure 3 provides a visual overview of the installation process of our fiber optic sensing system on Grist Bridge. Let's take a look. Figure A shows our UML team working on the girders in the parking lot before the girder is installed under the bridge. And Figure B is the side view of the bridge girder. As you can see, the girder is very narrow. The width is only 27 centimeters and barely fits a person to work inside. Figure C is installing and organizing the fiber connectors and protecting them during the installation of the girder. Figure D is a picture that indicates the position of our optic sensing system inside the first girder of the grist mill bridge. Over 4 years, we recorded the strength distribution of the bridge without traffic annually. Figure 4 illustrates the configuration of sensing textile, where the initial 21-meter segment represents the first section of the U-shape. In contrast, the subsequent 25 to 46-meter section constitute the remaining part of the U-shape. The strength distribution profile was reconstructed from the Boolean frequency response collected by BOTDA. To account for temperature fluctuations that can impact the Boolean frequency, we have calibrated the temperature coefficient of the sensing textile in our lab. By introducing the temperature compensation, the crosstalk of the temperature can be addressed. Our analysis of strength distribution baseline over the 4 years revealed no significant changes. This finding strongly suggested that the bridge did not undergo any noticeable structural alternations during this time. As we conclude, it is essential to highlight that the potential application of our research beyond this specific bridge. The technology we have developed has the potential to be applied to various structures, including buildings, pipelines, and more. Additionally, our work opens doors for future research in optimizing and expanding the use of fiber optic sensing technology. I would like to extend my heartfelt gratitude to the TIDC of University of Maine for providing funds for this research. Additionally, I would like to acknowledge our cooperation with Saint-Gobain Research North America. In closing, I would like to invite any questions or discussion for this from the audience. Your insights and feedbacks are invaluable as we continue to advance the field of structural health monitoring. Thank you very much for your attention.